Welcome students to the last module of hydraulic engineering course. In this module we are going to study in viscid flow, a typical application, that is wave mechanics. We are going to study linear wave theory, the derivation of velocity potential from scratch. We will also look at the boundary value problems, and so to get started with that, we will first see what the linear wave theory is. So let's start with that. So linear wave theory, what is that? As the name indicates, the linear wave theory can be guessed as when the waves are considered linear in nature. So the background is, as everybody knows, that the real water waves, have you seen waves in the ocean? So the disturbances that traveling in the ocean are actually waves. They might not be linear, but they are waves. So the real water waves, they propagate in viscous fluid. So the fluid in which it propagates is viscous, like water. Mostly it propagates in water. So, and water is a viscous fluid, and it propagates over a irregular bottom of varying permeability. All right. So that is the real case scenario. However, we assume that the main body of the fluid is irrotational, because the viscous effects, what we have learned in the our laminar and turbulent and viscous fluid flow classes, is that the viscosity effects are limited near to the bottom. So the bottom, above that bottom part, the main body of the fluid is irrotational, right? And what is the reason? Because, as I said, viscous effects usually concentrate in thin boundary layers near the surface and also the bottom, because the boundary layer will also be there at the surface. Since water can also be considered reasonably incompressible, we can assume the existence of a velocity potential and stream function. All right. So going back to the basics, you remember, if we can say that water is incompressible, then there will exist a velocity potential and stream function for an inviscid and irrotational flow case. Recall your lectures from viscous fluid flow. So before we go ahead and start learning about linear wave theory, there is a very important concept that is called boundary value problems. This is not only important for this particular chapter, but any problem that has something to do with boundary values. For example, we saw in the last week lectures on CFD that boundary values are some of the things that must be specified for the computation to start. So we look in this part very closely at these boundary value problems. So the formulation of boundary value problem is simply the expression of a physical solution in a mathematical form such that a unique solution exists. Okay, so what happens is, if there is an equation that is valid for entire domain, entire area, and then there could be infinite number of solutions to that problem, right? For example, let's say there is y square plus x square is equal to plus z square is equal to, let's say, 9. All right. So very simple to assume one of the solutions could be x is equal to 0, y is equal to 0, and z is equal to 3. This is one solution. The other solution could be x is equal to 3, y is equal to 0, and z is equal to 0. Another solution could be x is equal to 0, y is equal to 3, z is equal to 0, and similarly there could be many other combinations. Just I have written down in form of the integers, x, y, z are integers, but there could be many solutions. All right. But boundary value problems, the formulation of a boundary value problem is important, so that there will exist only a unique solution for one particular value of boundary. This equation will have one unique solution. There cannot be any solution. Let's say if we specify for x square y square plus z square is equal to 9, and sort of a boundary value we say just x, if we are given that y is 3, then it will have only one unique solution in terms of real number, x is equal to 0 and z is equal to 0. I mean, this we cannot exactly say this is a boundary condition, but trying to give an analogy that because of this boundary value there will exist a unique solution for a mathematical formulation, otherwise there could be infinite number of solutions. All right. Now, what are the steps to formulate the boundary value problems? First is we have to establish a region of interest. So, where are we going to apply that boundary value problem? We have to determine. For example, a region of interest could be a wave tank or a tank where the water flows. Secondly, we have to specify a differential equation that must be satisfied within the region. Thirdly, we have to select one or more solutions out of infinite number of solutions which are relevant to the physical problem under investigation. So, if there is an equation here, if we have specified a differential equation in the domain, then the solution that of that differential equation could be infinite, right? There could be many solutions, right? But we have to select only one or more solutions to the physical problem under investigation, and this is done using the boundary condition. This is exactly what I told you a couple of minutes ago. So, we have to reject those solutions that are incompatible with these conditions. All right. So, this actually is called the implementation of boundary condition. So, the steps to repeat again is, the first step is we have to specify a region of interest. Secondly, we write down the mathematical equation or a differential equation that must be satisfied in the entire region domain. And third one is that we have to select only one or more solutions, let us say 1, 2 or 3 solutions out of infinite number of solutions that are relevant to the physical problem, the real problem, and this is done by using boundary condition. A very simple example is, let us say a river, for example, right, river or ocean or wherever, and what we say, a part of river or ocean, the channel okay. So, this is something like this where the flow is coming like this. We know for sure, as we already read in our CFD class, that continuity equation and Navier-Stokes equation written by NS equation are two such differential equation that must be valid in this domain. Now, this will have infinite number of solutions, so we must provide a boundary condition. A boundary condition like that the water entering here has a velocity, let us say 3 meters per second, here there is a wall, this is open boundary. We can either specify a top free surface or even a wall here. So, what I mean to say, these are the boundary condition that will determine that there will exist a unique solution. Now, in addition to the spatial boundary condition, as I said, so this is, let us say, inlet, outlet, wall, for example. So, these are the so inlet here where velocity is given like 10 meters per second or something. So, apart from this, these are called the spatial boundary conditions or geometrical boundary condition, but there will also be a temporal boundary condition. So, boundary condition in time. that boundary condition in time is called initial condition. So, initial condition is nothing but a boundary condition in time. So, for example, we say at time t is equal to 0, the entire fluid was at rest. So, this means that V is equal to 0 at t is equal to 0 becomes our initial condition, all right, and this should also be specified. Now, under the assumption of irrotational motion, an incompressible fluid, as learnt in our viscous fluid flow class and the basics of fluid mechanics, kinematics, that there will exist a velocity potential which should satisfy the continuity equation. So, what are the assumption? Irrotational motion and incompressible fluid, there exists a velocity potential phi from our basic fluid mechanics classes. That means del dot u is equal to 0. Let us call this equation 1.a, or we know that if there exists a velocity potential phi, then u can be written as del phi. So, putting this here, we will get del dot del phi, and this is nothing but del square phi, which means del square phi by del x square plus del square phi by del y square plus del square phi by del z square. We call this equation number 2, all right. So, if you follow, we have got del square phi is equal to 0. So, if we consider the flows which are non-divergent and irrotational, so the previous equation was nothing but Laplace equation, right. So, for a non-divergent and irrotational, Laplace equation also applies to the stream function. So, we have seen for the velocity potential, Laplace equation which is del square phi is equal to 0 is Laplace equation holds good. All right, but so for the flows that are non-divergent and irrotational, we say that Laplace equation can also be applied to stream function. How? We are going to see. We know that for irrotational flow we have del w by del x if we consider a flow in u, so x and z direction, all right. There are two directions that we assume, there is no flow in y direction. So, the stream function as it can exist only in 2D can be written as del w by del x minus del u by del z, because the flow is rotational, all right. Now, using the definition of a stream function, if u is minus del phi del z and w is del phi del x, and if we put this, so we say del w by del x minus del u by del z is equal to 0. Instead of w, if we put here, so it becomes del psi del x of minus u is here, so it becomes del u del z by del z is equal to 0. So, it becomes, so this is with minus sign, all right. So, it becomes del square psi by del x square plus del square psi del z square is equal to 0, and this is what in 2D plane, this is all again Laplace equation, all right. Okay. So, repeating that, So this gives us Laplace equation in 2D, which is given by equation number 3b. Now the above equation, as I said, if you remember the boundary condition analysis, we said that the differential equation that we have formed should be valid in the entire domain of the fluid. So in the current analysis, what are the two equations, what are the equations that we have devised that holds true in the fluid using continuity equation? We have said that this equation, Laplace equation, above equation, that is Laplace equation, must hold throughout the fluid. All right. So at this point I have a small question to you, think about it. What if the flow was frictionless, okay, but rotational, not irrotational? What could the equation 3b look like? So what could be this equation? If you brush up your mind, for irrotational flow this term was 0, right? But if it is rotational, then it is given by vorticity W. So del square phi is written as omega, which is equal to the vorticity. All right. So this will be the resulting form of equation. Right now for irrotational flow we got 0, and this is true for rotational flow. All right. Now we know that the velocity potential can be defined for 2D and 3D. 2D means 2 dimension and 3D is 3 dimension, whereas the definition of the stream function is such that it only can be defined for 2D and 3D if and only if the flow is symmetric about x axis. So we know velocity potential is valid for both 2 dimension and 3 dimension. However, the stream function is valid only in 2 dimension. Okay. A special case in which we can still write it in 3D is when the flow is symmetric. Let's say there is a flow, okay, in x and y plane. This is x, this is y, and this is z. All right. So it's happening, but say this is so large that the variation in y direction is not there. So actually the flow is symmetric. All right. Therefore mathematically it will again be called as 2D because the flow is symmetric about an axis, and therefore we can still write stream function for such type of flows. The second thing to note is that Laplace equation is linear, that is, it involves no products and thus has a valuable property of superposition. So we don't have terms like delta x, delta y, or phi 1 in is not there. So we in a different sense we say that Laplace equation is linear because it does not have any product. Therefore we can apply the property of superposition to Laplace equations. So what is that, this superposition? If we say if phi 1 and phi 2 are the velocity potentials and each of them satisfy Laplace equation, then we can define another velocity potential phi 3 which are a combination of phi 1 and phi 2, that is a phi 1 plus b phi 2 will also satisfy the Laplace equation. Okay. So any combination of phi 1 and phi 2 will satisfy Laplace equation if phi 1 and phi 2 each satisfy Laplace equation. The reason is that Laplace equation is linear and it does not involve any products and therefore can be superimposed. So one important property is kinematic. We are talking about boundary conditions. So one of the important property is called kinematic boundary conditions. all right. What is our KBC? At any boundary, whether fixed or free, certain physical conditions must be satisfied for fluid velocities, and these conditions on water particle kinematics are called kinematic boundary condition, all right. At any surface or fluid interface, there, for example, this is one of the example, at any surface or fluid interface there must be no flow across the interface. For example, if there is ground here, the boundary kinematic condition will be the velocity w is going to be 0 in the downward direction, or if there is a water surface, here also the water will not have any velocity, otherwise if it has a velocity then it will still be water there, right, then there is not going to be any interface. So, at any surface or fluid interface there must be no flow across the interface, and that is very a standard universal type of kinematic boundary condition. So, this is quite obvious actually in case of impermeable fixed surface like sea wall. Mathematical expression of kinematic boundary condition may be derived from the equation which describes the surface that constitutes the boundary. So, now we talked what the kinematic boundary condition is. Now we have to find what the mathematical equation for such boundary conditions are, and as said, these kinematic boundary conditions can be derived from where? Derived from the equation of the surface that constitutes the boundary. So, if we define a surface, we can determine the kinematic boundary condition. We will understand this with an example. How? So, we say that any moving or fixed surface, let us say if it is written by, so this is the equation of the surface f, how it is dependent on x, y, z and t we do not know, but let us say there is a function f x, y, z comma t is equal to 0. So, let us take a real life example of sphere. A sphere let us say has a radius a, so f of x, y, z comma t can be written as x square plus y square plus z square minus a square is equal to 0. Let us say this is the surface of the sphere. So, for such surface to represent an interface, the total derivative or material derivative of the surface would be 0 on that surface. This is what our definition is, that there should be no flow across the interface, which means that the total derivative or material derivative of the surface would be 0 on the surface, all right, because there is no flow across that. So, what we do is capital df dt material derivative can be written as del f del t plus u del f del x plus v del f del y plus w del f del z. Let me use a laser pointer. So, del f del t will be equal to, sorry, df dt, whole df dt will be equal to del f del t plus u del f del x plus v del f del y plus w del f del z. And what does this say? The total derivative at the surface. So, on f is equal to 0, which means surface should be 0, right here, all right. Or in other words, we can say because this is 0, all right. So, if we bring it on this side, we can write minus del f del t is equal to u dot del f, all right, a representation in a vector form, all right. So, this is an important equation. Now, if we define a unit vector normal to the surface, so a unit vector normal to the surface can be written as, right, so normal to, if you recall your mathematics class, this is a unit vector which is normal to the surface. Using this n, we can write equation 5b, this thing, as minus delta f del f del t is equal to u dot, simply what we did, instead of delta f I will just, so if we use this equation, we just substituted n mod delta f. We substituted this in equation 5b and we get this value. All right. Or we can write, if we want to write u dot n will be nothing but, if we just what we do is we just bring this in the denominator. All right. So we get an equation u dot n is equal to minus del f del t by mod of delta f on f x y z t is equal to 0. All right. U is a vector and n is a normal vector. So here delta f is nothing but simple delta f by delta x whole square plus delta f by delta y whole square plus delta f delta z whole square. Now if you look at the condition here, u dot n is equal to minus del f del t by mod of f. This condition requires that u dot n, that is the fluid velocity normal to the surface, this is u dot n, correct, should be related to the local velocity of the surface. Del f del t is the local velocity of the surface. By this equation, the one that we wrote before. Let us say if the surface do not move, that means that it is fixed, all right, with respect to time, that is the local velocity of the surface is 0, that means u dot n was minus del f del t by mod of f, right. If it does not move, then this is 0, which means u dot n is equal to 0, or in other words the velocity component which is normal to the surface is 0. And we have seen this, that when we assume a fixed surface like the river bed or the sea bed, you remember I drew a diagram and said the velocity here will be 0. We just used to say that, but now we have proved this, okay, that the velocity component normal to the surface will be 0. All right. Now we start with the bottom boundary condition. I think this is a fine place to start. In our next lecture, we will start with this topic called the bottom boundary condition. Until that time, thank you so much. I will see you in the next lecture.